Alright, let's take a look at some of the things that we're working on in class regarding writing these chemical formulas. We're talking about binary formulas. Remember, we're talking binary, and that simply means I have exactly two ions to work with. Binary means two, and we also have a few different kinds of bonding that we're talking about. And we're talking about ionic, which remember is a metal and a nonmetal. And we also have covalent, which is two non-metals bonding. And they work in slightly different ways. So I'm just going to go through worksheets 56 through 59, a little bit at a time, and we'll take a look at how to work each of those types of bonds. I'm going to start with page 56. Remember, on worksheet 56, this is talking about covalent bonds. And I'm going to look at one, I'm just picking at random right off of the page. NO2. I want to know the name of this molecule. It's a covalent bond. Nitrogen and oxygen are both nonmetals. So I'm going to use the covalent bond prefixes. And you need to remember where to find those charts in your chapter. I look at nitrogen. There's only one of them. So I'm simply going to write nitrogen. Remember the rule, we do not put mono on the first element. Then I look at oxygen. I notice that it has two. And the prefix for two is di. And remember that the last element will always have IDE at the end. So oxygen becomes oxide. So this formula, NO2, we call nitrogen dioxide. All right, I'm going to take a look at another one. Going to look at SO3. We have one sulfur atom. And remember, we do not use mono, so I simply call it sulfur. We then have three oxygen atoms, and the prefix for three, that is tri. So I simply write trioxide. So SO3 is trioxide. Now you'll notice on the polyatomic ion chart, this also has its own special name that we call sulfite. So we could actually call it either one by using the covalent bonding rules and the prefixes, or the name for that particular bond is called sulfite, SO3. Okay, what if I have a subscript with the first atom, such as P2O5? Well, the first atom, since it has a 2, it's not mono, so we don't have to worry about it. It is di. And remember what element P is. That is phosphorus. Just takes a moment to write out. It actually takes longer to write these out than it does to figure out what to do. And the prefix for oxygen is penta. So I would simply write pentaoxide. Well, we normally don't run an O and an A together, so I'll just take off the A, and I can call it diphosphorus pentoxide, P2O5. All right, let's quickly review what those prefixes are. For one, it is mono. 2, the prefix is di. 3, tri, like a tricycle. 4, tetra. 5, think of pentagon, penta. And 6, we don't see this a whole lot in our class, but that would be hexa. It could come up, but we don't use that a whole lot. So those are your prefixes. So let me do one more example of the covalent bonds. I'm looking at N2. I think I've already done that. So I'm looking at PCl3. Only one phosphorus, and we don't use mono on the first one. So I just write phosphorus. I have the prefix 3 and the element chlorine. So I say trichloride. So we use the covalent bonds. We need to remember something. Only the covalent bonds of two or more nonmetals, and in our case binary with two nonmetals, gets the prefixes. If we have an ionic bond, we don't do that. And I'm about to show you what we will do with an ionic bond. Alright, so now in an ionic bond, remember that the two parts involved in an ionic bond, we have a metal and a nonmetal. So if you look at the formula, if you see a metal, and it will always be listed first, we have an ionic bond. We don't use prefixes. And also NH4, even though that's two nonmetals, well, it pretends to be a metal ion that will give away one electron. So we'll have an oxidation number of +1. Now remember the oxidation number, that means what will that ion do with the electrons? Those that give away, usually the metals, they'll be positive. And those ions that take those electrons, they're going to be negative. So I'm looking at now an ionic bond of magnesium and chlorine. So remember, the magnesium, you look at the oxidation, or you may remember, since it's in group 2A, it has an oxidation of +2. It'll give away 2 electrons. Chlorine, a halogen, will take 1 electron. So it has an oxidation number of -1. We use these numbers to figure out the subscripts, how many of each we need. Now, you have to remember that we need a grand total of 0 for a neutrally charged molecule. Well, magnesium is +2. Well, we need chlorine then to be -2. So we simply ask, how many -1s does it take to make it -2? And that answer is 2. -1 times 2 is -2. So when I add these together, I get the 0 that I'm looking for. All right, one more time. I'll go through that one more time. Magnesium has an oxidation of +2. And chlorine has an oxidation of -1. I need to get a total of 0. Well, I ask myself, how many -1s does it take to match up with a +2? And the answer is 2 of them. -1 times 2 is -2 with the +2, and together that's the total of 0 that we want to use. So you see, I'm just using those oxidation numbers to help figure out how many of each atom or ion that we need. And let's do one using a 3. Aluminum. Aluminum's oxidation number is +3 because it will give away 3 electrons. And I'll match it up with bromine. And I'm going to make a compound called aluminum bromide. Bromine is a halogen, and it takes 1 electron, so it's a -1. So my question is, how many 1s does it take to make a 3, so my positive and negative will cancel? And that is 3. Now total for aluminum is +3, and total for bromine is -3. That gives us a grand total of 0. So our formula for aluminum bromide is AlBr3. And that will work even if it's the metal that needs to be increased. So I'll try one of those very quickly. I'm going to look at something like hydrogen and sulfur. Now I'm going to make a compound called hydrogen sulfide. Well, I look up the oxidations on my charts. I see that hydrogen is +1 because it'll give away an electron, but sulfur is -2. So it works just the same way with the positive side that it does the negative side. How many 1s does it take to make a 2? It takes 2 of them. Now hydrogen's a +2, sulfur's a -2. We have a neutrally charged molecule of hydrogen sulfide. It really is that simple. Sometimes, though, we don't get a perfect matchup, and I'll show you what I'm talking about. We may have something like aluminum with a +3 and oxygen with a -2. Well, there are 2 ways we can go about this. See, I can't just say 2 -2s will make up 3 because it doesn't work that way. That would be 4. And there's no way to just increase one to match the other. Well, we have 2 ways. Long way first. The least common multiple of 3 and 2 is 6. So I'm going to make them both equal 6, positive and negative. Well, how many 3s will make a 6? 2 of them. How many 2s will make a 6? 3 of them will. Now I have positive 6 and negative 6, and that is 0. And I'm going to clear this off and write aluminum oxide again and show you the short way to do it. Now you got to remember, shortcuts are nice, but they work only under certain conditions. And in this case it'll work because it's binary. Aluminum is plus 3, oxygen is minus 2. Remember from the notes I gave you this little switcheroo trick. So here's how that works again. This 3 is going to come on down here to the bottom of the O, and we take off the plus sign. This negative 2 will come on down here to the bottom of the aluminum, and we take off the minus sign. So we have Al2O3, and if we add up the oxidations, it'll work. Add up those oxidations. I'm going to darken these numbers now so you can see them better. 2 and 3. Positive 3 twice, that's positive 6. Negative 2 3 times, that's negative 6, and we get a 0. So if we don't have a nice even jump from one to the other, what we do, we simply find the least common multiple of the 2, or we could do our little switcheroo trick, and it will work out. Alright, getting close to the end of this video, let's look at a polyatomic ion now as a binary compound. What if I have calcium and hydroxide? Now you need to use those polyatomic ion charts to know what I'm talking about here. Polyatomic ions I will always put in parentheses. That way I know. If I see 2 capital letters like O and H, that's polyatomic. That means 2 atoms pretending to be 1. So let's look at the oxidations. Calcium is positive 2 because it gives away 2 electrons. Hydroxide is negative 1 because even though those 2 atoms have combined, there's still room for another electron. It works exactly the same way as the single atom of chlorine did in a previous example. I still want to get my grand total of 0. Calcium is plus 2. Hydroxide is negative 1. It takes 2 hydroxides to make a negative 2. I match that up with my positive 2 for calcium. I have my grand total of 0. So my formula is calcium, Ca, hydroxide, OH, 2. So it is CaOH2. I'll try another polyatomic ion now. I'm going to do sodium phosphate. Na is sodium, PO4 is phosphate. And again, I need to know about the oxidation numbers. For sodium, it is plus 1. For phosphate, look on your chart, you'll see it's negative 3. My little switcheroo trick will work, or I can say, how many 1s does it take to match a 3? And that answer is 3 of them. So the formula for sodium phosphate is Na3PO4. Remember, we don't go inside and do anything to the numbers or the letters in the parentheses. Remember what we said in class. Don't go in there. They don't want you. They will mess you up. Keep everything on the outside. Never change a letter or a number inside those parentheses. In fact, just stay out of there and all is good. And just to show you that polyatomic ions work the same way as single atoms, let's do one more. Just to remind you here. We're going to do the compound called, looking on the worksheet, I'm going to do, let's do, okay, so I'm going to do the formula for lead. PO4 is phosphate, so I'm going to do lead phosphate. This is straight off one of the worksheets we did, and we're saying that lead is going to use the plus 4. So it's going to share 4 electrons. And phosphate, its oxidation is negative 3. Again, I'm getting these off of those charts that I gave you in class, and they're in the book. Well, I cannot just say 2 phosphates will make a positive 4 match a negative 4. That won't happen. So again, I'm going to use the LCM of 4 and 3, and that's 12. So to get lead to be 12, how many 4s will make a 12? That's 3. For phosphate to be negative 12, how many 3s make a 12? And that's 4. And once again, you will see that really the shortcut is nice, but you have to remember it's nice only because the LCMs make the oxidation numbers work. So there, that 4 switches down here, that 3 switches down here. Our switcheroo trick works for the polyatomic ions just as it does for the single atoms. So hopefully this is helping. If not, make sure you speak up in class because we'll have plenty more examples and I want to make sure everybody has it. But as far as using the covalent bonding and ionic bonding rules to write the formulas from the symbols and oxidation numbers or prefixes, this is all we need to do. All right. Hope you learned something from it. Hope you enjoyed it. We'll see you in class.